Hello, I'm Youngju Ji at Code Vision. I will be presenting our research on the deep learning-based cat lifecycle adaptive health monitoring system. Here's the outline of our contents. Introduction, our methods, classification experiment, and then the conclusion. As more and more households are keeping pet cats, the number of multi-cat households is increasing. Consequently, to manage the health status of individual pet cats, cat identification research is being conducted to individually monitor the cats. One approach gaining attention is the use of contact-based methods, where devices like beacons are attached to each individual. In contrast, non-contact-based methods mainly use cameras, gaining significant attention too. By utilizing cameras and computer vision techniques, it becomes possible to identify individual cats without directly attaching any devices to them. We'll focus on non-contact-based method and approach by the machine vision side. For non-contact-based method with camera, a machine learning model can be exploited to monitor and identify each cat. However, when the cat's physical appearance changes over time, the machine learning model may not properly recognize the individual when it is trained with all images of them. So, when a remarkable physical change happens, the identification may become inaccurate. To address this challenge, we designed an adaptive monitoring system with camera for physical changes of cats that utilizes cloud servers to retrain the cat identification model. By leveraging the cloud computing, we can update and refine the cat identification model based on new data. This approach allows us to adapt to changes in the cat's appearance and improve the accuracy of the system over time. Our system consists of two parts: cat health monitoring system, and the another is model retraining. The cat health monitoring system is composed with litter boxes where cats enter and leave, and a cloud server that enables retraining. Then, the model retraining section is divided to embedding vector selection and fine-tuning of the model. So firstly, I will go into more detail about cat health monitoring system. In an overview, the system consists of a cloud server and a litter box. The litter box is equipped with an embedded computer and a camera. The camera monitors the cat, and the embedded computer sends the cat images to the cloud server when a cat is detected. The cloud server is equipped with an AWS G3 instance, which includes the feature extractor, efficient V2B0, and the classification model, K nearest neighbor, KNN. The embedded computer detects and records during the entry and defecation activities in the litter box, and finally, the living. When cats are detected, images of those are transmitted to the cloud server. Various CNN-based object detectors can be used for cat body detection. The server classifies the class of the detected cat with feature extractor and a classifier. A feature extractor outputs an embedding vector from the transmitted body image. Then, this vector is classified using a machine learning-based classification algorithm. We construct the classifier of the server using efficient V2B0A and KNN. To be combined, an object detector detects a cat and sends the detected images to the server. The server then extracts features and classifies the individual cat with machine learning models. Next, I will introduce how this server retrains the model. The model retraining is designed in two steps: embedding vector selection and fine-tuning. The embedding vector selection is for adapting to slight physical changes, while fine-tuning is for a noticeable change over time. The embedding vector selection is automatically done without queries to users, except for the first time. But fine-tuning always requires users labeling. Before we get deep into each process, let's look at users' initial registration. Initially, the user manually inputs the cat images to the server from their phone and so on. This enables the server model to initially classify the detection results from the litter boxes. However, these images are discarded after the vector selection because the system uses images from litter boxes, not by users' phones, and etc. Whenever a certain number of litter box acquired images for a cat are collected, a mean vector is calculated from both the existing embedding vectors and the vectors of the new images. And then the mean vector is shifted by the new embedding vectors of the images. Then only the embedding vectors closest to the mean vector are selected, and the remaining vectors are discarded. In this process, the model can gradually adapt to slight changes in appearance. It is also automatically done without users relabeling, except for the first time. Only for the first time, the user is asked to label the class of each cat because the dataset is being changed from user registered to litter box acquired. Whenever a sufficient number of images for all cats have been collected through the litter box, the feature extractor is fine-tuned. The user performs relabeling, and the server's feature extractor is fine-tuned using the relabeled dataset. And finally, new embedding vectors are again extracted from training sample images for KNN through the fine-tuned feature extractor. This fine-tuning makes the model adaptive to noticeable changes in appearance. Next, it is our experiments. It was conducted using an Amazon EC2 G3 instance with an NVIDIA GPU. The entire code was written in Python 3, and the classification model was implemented with PyTorch with CUDA and scikit-learn on Amazon Linux too. The dataset consisted of 7,162 training images and 1,772 test images acquired from 36 cats. These images were collected in various environments, such as indoors and cat cafes, and so on. The images were processed with bounding boxes and used for training the model. Based on the performance testing conducted for cat individual classification, it was observed that the KNN algorithm demonstrated exceptional performance when the value of K was set to 5. In summary, we designed the cat monitoring system adaptive to change in appearance of cats by using a cloud server and by retraining a model. We designed the retraining algorithm for identification model. And the experimental results showed 93.91% of accuracy with setting K to 5 in the KNN algorithm yielded best performance for cat individual classification. Overall, the cat lifecycle adaptive health monitoring system provides an adaptive and reliable solution for individualized cat monitoring throughout the pet cat's life. Thank you for listening.